doing well. So continuing on our journey, today we will be trying to understand uh the basic components of a thread. Okay, so we are dealing with threads, right? You are dealing with threads. So today we would try to understand basic component. Like we're going to break down the thread into its basic components. Contrast thread, and then we will see a little bit about benefits of designing and drawbacks of having a multi-threaded system. So multi-threading or a multi-threaded system is what we are trying to understand. Then we'll look about fork join. We'll look about thread pools, fork join, and grand central dispatch. So we'll see about fork joins, grand central dispatch, and we will also try to understand about thread pools. What is thread pooling? Then we will see about Windows and Linux OS representing threads. So Windows and Linux OS. And then the last topic that we would be covering here is pthreads, Java, and Windows API. We'll see how multi-threading is going to happen in these places as well. Before we go on, let's make sure our okay, I know what's up. Yeah, let's make sure our stream is up and running so that there is no at times Twitch behaves. Oh yeah, here we go. Yeah, so everything is as expected. Now let's go. Okay, so first basically, let's see an overview. Now, thread is a basic unit of CPU utilization. It comprises a thread ID, a program counter, a register set, and a stack. It shares with other threads belonging to the same process its code section, data section, and the OS resources such as files and signals. A traditional process has a single thread of control. If a process has a multiple thread of control, it can perform more than one task at a time. Oh, so let's see. Let's have an overview about threads. So overview. So threads is going to be the smallest part of a process is a thread. The smallest unit of a process can be a thread. Is a thread. Now a process can have a single thread, or it can have multiple threads, or it can be multi-threaded. Now whenever you assign or whenever a thread is created, so each thread will so a thread will get its own okay, it's right here. A thread, it will get its own thread ID. It will have its own program counter. It will have its own set of registers. Then it will have what you say a stack. Um, Now, basically, most software applications that run on computers and mobile devices are multi-threaded. Also, I mean, let's see a little bit about thread structure so that we can visualize what is going to happen. So a thread is going to get its own the smallest unit of execution within a process. So we'll have a thread ID, we'll have a program counter, we're going to track the next execution thing. We're going to have a stack, then we are going to check the state, then we are going to be having scheduling information something. Okay, so how does thread interact with the process? Now how does a thread is a process like a house and threads are the people. So now we're going to have one thread. If it's a single threaded environment, we are going to have okay, so the thread is going to take things from the process. Does it look the thread is going to take things from the so if the process switches, then we need to store the thread things as well. So thread is going to take things from the processes. Okay, I got that. And the thing, one more thing is, so when we make a process switch, the thread state also needs to be stored. Yeah, so basically a process is created, it starts with the main thread. Okay. So let's see a diagram. So this is our process, right? So every process, if you see, okay, let's come back to the main thing. Yeah, so every process is going to have two things. So one is you're going to allow them a set of registers to store, and then here you are going to add, for example, code segment. This is my code segment. This is my data segment. So here I have data, and then I'm going to have files over here. So this is my now then one more thing. Okay, and then this is my register. So you're going to have set of registers. So you have and then this is my program counter, and then I have a stack. And then this is so below that I'm going to have my thread being present here. This is my process, right? Process below. So all threads are going to take things from the process. The moment we switch the process, or uh, the moment we switch process, thread state is also stored. So okay. Now in a multi-threaded environment, we'll be having a multiple threads instead of a single one. Okay. So the advantages of a multi-thread is first is resource sharing, speed is faster. Now there is something called as so now to have multi-threaded or a multi threaded system, we need to have we need so okay the uh, earlier in the history of computing design, response to the need for more computing performance, single CPU system into multiple CPU. A later yet similar trend designed to place multiple computing cores on a single processing chip, which refers to such as multi-core and multi-threaded programs. Okay, so if you see the stage of evolution, you added a one single core. Sorry, one single. This is like a CPU plus a ALU, only one. This is when we had 8086 processors, the most famous one. Then we went to having, oh, instead of having a one single processor, we said let's have multiple processors. Then, so for example, this is the Xeon Intel motherboard, right? So you have one, this is CPU ALU, this is two CPU ALU. These are two independent processors, and to have data, you need this bus for between communication. But then now, even this leads to cost, right? The cost is more, and having two processors or power consumption is more. So now later on, what they came up is we have one single chip, but then on that single chip, we have multiple cores. Each core is going to represent a single, okay, is going to be a single unit, and uh, so I'm going to have a CPU ALU thing. Um, these are all individual CPU and ALU. The distinguishing factor is these are all on. So this is one chip. This is one chip, and all of them are on one single chip. So this is CPU ALU again. This is CPU ALU again. This is CPU ALU again. Okay, now this is what is called as multi-core. So instead of, so what does it do is, so the advantages is, so if it was a different CPU, you have to go from one chip to the another, right? So time is spent over here. But then since it's on chip, it's even more faster. Buses are on the chip, right? So even more fast communication between them. The speed is more. So yeah, speed is increased over here. Now this gives rise. So what we can do is, so this leads to something called as a multi-threaded environment, right? So you could have a multi-threaded. Basically, you run individual threads on these cores. Now, which core decides what? So that is again scheduling, right? You cannot define which thread or which. That is all based on the scheduler. Now, then, so to define that performance, we call something called as the Amdahl's law. Is a formula. So Amdahl's law is a formula that identifies potential gains from adding additional computers to application that has both serial and non-parallel components. If S is the portion of the application that must be performed serially on a system with n processing cores, so then I'm going to, so there is, then came something called as Amdahl's law, and we are going to calculate the speed based on M. So this is Amdahl's law. Basically, it's a graph that indicates how my um, speed is going to increase as we have more number of cores. So I can say the formula says speed up is less than or equal to 1 upon s plus. So for example, uh, when we were reaching to micro components, so how many components, there is a formula, right, to uh, like to reduce the size you need to add 4 type of components, something like that. I don't know the exact thing, but uh, now this is as an example. As we assume we have 75% parallel and 25% serial. If you run this application with 2 processing cores, so n is basically the number of cores here. This is cores, and then s is the portion of the application. So s is going to be okay. So what we are saying is, out of the total percentage, so this is my 100% processing. So that s is going to say, I'm going to define that. So s is basically an indication of serial. How much is serial processing and how much is non-serial over here? This is non-serial percentage. This is what is my s indicating. For example, if 50% of an application is performed serially, the maximum speed is 2 point. That means if I say, okay, if I say 50% is serial and 50% is non-serial, right? Then by this calculation, so the only thing variable is this, right? So if I have, suppose I have 4 cores over here, then this formula will become 1 upon 50 plus 49 by 4, right? Something like that. Now let us see that as we are as is approaching infinity, right? So yeah, as we make this as so as this, so this is, so as this approaches infinity, so 1 upon infinity, this becomes, the whole thing becomes tending is to 0, right? So then we get 1 by s speed. So as this tends to infinity, we say, yeah, this is just a randomized assumption. So this n is tending towards infinity, so then the formula will have 1 by s. Speed is going to become 1 by s, right? So this is how basically we are going to say how the Amdahl's law works. Now programming challenges, now trend towards, so now when we have multi-core systems, this is what are the challenging that we need to go. So when you have a multi-core system, first is we need to identify areas that can be divided into separate tasks, like whether we need a parallel okay. Now with the advent of multi-programming, right? So our goal is with the advent of multi-cores, as a app developer, what are the challenges that we face? First is we need to identify tasks. Now by identify task, what is trying to say is we are going to check if it is serial or non-serial. The next thing that we do is we need to do is concurrent processing actually needed here, and which task should be queued in for non-serial processing. Now balance, by identifying tasks that can run in parallel. Now programmers must also ensure that the task performs equal work, so we need to maintain a balance, right? So suppose if we divide a program, we need to make sure it's balanced out, that there is we're not assigning 100% of task to our serial and making the non-serial process to be, it's like a what do you say, deprivation, right? Or a starvation thing. We don't want that to happen. We want the threads to be or the multi-programming to occur in a very efficient way. The data splitting, just as the application are divided into separate tasks, the data access and manipulated by the tasks must be divided to run on separate code. So again, we need to split the data, and then we need also something called as data dependency. So splitting data is one thing here. Okay, let's see. Splitting data is one thing. And then data dependency, the data accessed by the tasks must be examined for dependency. So data dependency, like whether whether suppose if we have two concurrent thing, right? So we are doing multi-programming. So something is running on core 1. This is my core 1 and this is my core 2, right? So we need to make sure there is no sort of dependency between them. We need to ensure that what uh, if there is some data sharing that needs to happen, so we need to manage that as well. Now then we need to, the last thing as always is testing and debugging, right? We should be able to test our programs. So testing is again a major thing. So testing and debugging, right? This is a major thing. Now parallelism. So parallelism, there is two types of parallelism. One, you have data parallelism and then it's task parallelism. Now consider, for example, summing the contents on a single core, a thread will simply remains. However, if it's a oh a parallelism can be so he's saying they can be okay, you can subdivide parallelism into two types. So parallelism can be further broken down into two things. Is it data or task? For example, if you have an array of size n, so what you do is you store 0 to n by 2 on one, and then you have n by 2 to the last on the other. So this is data splitting. On similar lines, basically, we are going to, when we ask about task parallelism, we are going to do about threads, right? We are going to have multiple threads being coming into existence. So fundamentally, data parallelism on distribution data, okay, a task, okay. Now, now multi-thread. Now our discussion has treated threads as a generic sense. Support for threads may be provided at, so either okay. Now right now we haven't, so our operating system is always divided into two parts, right? As we say, so one is like a kernel space. So one is a kernel, oh sorry, user space, and then is my the other is my kernel space, right? So based on, either you can have threads over here, so threads operating in user space, or you can have threads operating in my kernel space. So that's okay. Now ultimately a relationship must be occur between user and threads. Okay. Now user threads are supported above the kernel and are managed without the kernel support, whereas kernel threads are supported and managed by the OS. Now these are, so user threads are not managed by OS, so this is not an OS functionality. Kernel is managed by OS. The kernel threads will be managed by the operating system itself. Ultimately, a relationship must exist between the user kernel threads. We look at the common ways of establish. Now, why do we need a relationship between user threads and kernel threads? So, why do we need? Oh, ultimately, it's the okay. First, let's see this thing. Why do we uh, relationship between user and kernel threads? Okay, now okay, so yeah, so although yeah, okay, now let's see this thing. Now now we need to understand, so why do we need a relationship between user and we are going to say why do we need a relationship? between user and kernel threads. So our goal is to identify why they should we have a relationship. Okay. Now user threads can't do everything on their own, right? So for example, if I need to access memory, right? So if you see the structure of the OS, so this is my kernel, right? The kernel has direct access to the hardware, right? So if there is anything that needs the access to the hardware, it has to go to the kernel, which is going to be managed by the OS. So hence, now these threads, then the user space will be created by the user in a program. However, to access the hardware, they will have to interact with the kernel thread, and then they're going to be so they're going to be we need a mapping between user and kernel thread, so let the kernel know how to run the user threads, right? For example, if there is any um what do you say, any hardware requirement, it's just the last thing is basically the kernel that is going to take the responsibility, right? So you can have three types of relationship. So let's go. The first is basically one to one. Okay, so first type is one to one. So when we say one to one, each user thread maps to maps to one kernel thread. So let's say, so you're going to have this space, and then so now what we are going to do is basically we are going to one mapping. So each user thread maps to one kernel. So this is my user thread, and then this is my kernel, right? So each user thread is going to map one to one. So this is exactly one to one mapping. Now this is used in Java threads, Swift concurrency. The advantage is true parallelism. Kernel handles the scheduling. Disadvantage is more overhead limited by the OS thread limits. Now why he's saying it's true parallelism? Like, let's see this thing. Okay. Oh, so it's basically at the end, it's the OS is going to schedule this thread, right? So okay. So I get what he's trying to say. Okay, so when we type above so OS not only schedules process but also threads. Like what's the difference in between them? The OS schedules both the process and the threads, but there's a key difference, right? So what is scheduled? Okay, handled by the OS. Oh, okay. So for example, yeah. So as we, yeah. Okay, I am saying what I am understanding what he's trying to say. Okay, okay, okay. So like the way scheduler we schedule a process, right? So these are processes present in the process queue. So I have P1, P2, P3, and P4, right? So this is getting scheduled by the OS. Now this OS also is going to schedule my. So when this is so, and we said that processes are made up of. So P1 is okay, and then we said on a final level, process is made up of threads, right? So I'll be having multiple threads in it, right? So when the scheduler picks P1, then the OS will also schedule which thread to run on which what do you say um which will switch between which what do so it's basically going to say like which thread to run on which CPU. So which thread to run. So this is the three thread. This is T1, T2, and T3. So I'm going to say T1, T2, and this is going to be my kernel threads that is going to get scheduled, not the user ones. So the okay, based on how we defining that user to kernel interaction, uh, okay. So first is basically yeah. So basically only the OS can access the CPU, right? So if there is any thread, CPU is the hardware, right? So it must go through the kernel. That's when user level threading are going to come on. So basically these are the kernel threads that are going to be executed, and based on what type of language or what modeling have we done, so we are going to model this user to kernel thread. That means the moment we create one user thread, it inherently it also, so the moment we okay, let's see, the moment we create a single thread, we also assign a kernel thread to it. This is basically one to one, and then why we are saying one to one here is why we are saying this is two parallelism is um, since each thread has its own kernel thread, the now okay. So CPU is going to schedule this thing, right? So CPU as is going to schedule. So what we can do here is, if you are having four threads, then no thread will be waiting, right? So suppose okay. So in my user space, I created four user threads. I don't know how to draw. Yeah. So suppose in my this I have four user threads. So then I have four kernel threads as well, right? That means, and when the OS is going to schedule these kernel threads on the CPU, they are going to work on individual computers, right? So this is my computer, so I'm going to have uh, CPU. Okay, this is going to be my core 1, core 2. and core 4. So basically, this is what now, since I have since the OS is going to schedule them, now the OS is going to achieve parallelism, right? Because I exactly have all of because all the threads now can be executed parallelly or can be done concurrency, right? So basically, this is what we said, that we have a 1:1 model. Now, then we have many to one model, right? So when we say many to one, okay, then we have, so now we said 1:1, then we have many to one, right? So many user threads. So this is fast. Okay, if a user threads block user thread, so many to one is, so the next type or the next relationship that we achieve is basically many to one, right? So you have many to one. So basically you have many kernel threads, so many user threads and one single kernel thread. So if there is any blocking that is going to happen, since in the, okay, yeah, blocking is something that is going to happen here. Why? Because ultimately here this is going to run a single thread and then I'm going to have multiple threads here. So blocking is going to happen is because this is going to be scheduled by OS, right? And all the suppose if any of this thread has something, a blocking operation, this is blocked. So that's a drawback, right? Now then we have many to many. Okay, now your blocking can be avoided, I guess. That is why we came up with many to many. So third is a many. So what we can do is now this is again it is a bit, the disadvantage is it's complex, but then that blocking thing is common. So I'll have one thread over here. This is my user space, and then this is my kernel, right? This thread can be mapped to 2 to 3 threads. That means if there is a blocking IO, we are going to put it in this. So basically, many to many is overcoming the drawbacks of many to. Uh, Overcomes 1:1. Oh no, when is 1:1, then okay. The problem is if I have more in user, you can create any threads, right? But then the kernel, there are only limited threads that you can have. Okay, no, I'm saying many to many overcomes. Okay, blocking in defect in one to many, right? So if you have, no, in many to one. That is a drawback, right? Because if you have that thing, then that, because we are going to have that many to many thing, right? Yeah, so basically that many to many is overcome uh, the effects of. Oh no. Oh, yeah, I can do this now. Major, so blocking is not a issue, right? So that, yeah, so when you have many to many, you can pause that thread, or you can just assign it to some other thread. You can do some sort of, you have more flexibility here, right? If there is any blocking IO, then you can get rid of it. So that is a good thing. Okay. Now thread libraries. Okay. Now a thread library provides program and API. So for now to create threads at the user level, we need something called as a thread API that is able to create the threads. The three main libraries in use are POSIX threads, Windows, and Java. Okay, now P threads. The thread extensions for the POSIX standard may be provided at the user level. Okay. A thread library and API for creating and managing threads. There are two primary ways. First is to provide a library in user space with no kernel support. The second is to implement a kernel level library directly by an operating system. Okay. And there are three major ways you do create threads. One is P threads. Oh, now are we dealing with threads at the user level? Okay, I guess this is what he's trying to say. Creating threads at user level methods. There are three major ways to do that. One is when you have the what do you say? Uh, no, using thread library, right? Yeah, so you have libraries. Yeah, so for example, yeah, you will have to have thread libraries. Okay. The next thing is basically how are we going to create threads? So creating user level threads. So first is you use the POSIX library. Then you have Java that has a inbuilt support for creating threads. And then there is this one more, oh, Windows API. Then you have this Windows API that can create threads. Windows threads. So these are the three major ways of doing thread creation. Okay. Now let's talk about Java threads. Right now, the threads are the fundamental model of program execution in Java. Okay, let's see the Java model, right? Okay. Let's come here. Let's see Java, or let's see about Java runtime. Java. Oh, Java does not have any async. It's all about thread management, right? Okay, so if you see how the Java runtime environment is going to look, now there is other fundamental problem in Java language, and its API provider itself of is for creation of management of threads. All Java programs consist of a single thread control. Even a simple must have only a main thread that runs as a single thread. Java threads are available on any system that provides JVM. The Java API thread API is available for Android as well. There are two techniques for explicitly creating. One is using the thread class to override its run method. An alternative and more conveniently is basically to define a class that implements the runnable interface. Okay. For example, now lambda expression. Later on, lambda expression came in place, right? Mm, okay. Now, Java has introduced several new concurrency features that provide developers with. Okay, let's see the runtime, right? Okay, let's come back to which. Let's go to Stream Manager maybe. Okay. Do we have a stream? Oh yeah, let's go to manage stream. Okay. Let's see. Let's see the Java runtime. And let's come here. Yeah, yeah, let's take dash. Okay. Let's go even down. Yeah, so this is basically my Java runtime, right? So as you see, you are already having this threading or thread pool present here. This is already present in the JVM. In Java is basically supports multi-threading. Async will happen using multi-threading, and then now this is at user level, right? So now with the continued core of growth of multi-core, okay, that is thread pool. Now there is something called as thread pool, right? Now this is from your things are going to go a little bit. Okay, we'll see what is going to happen here. Okay, so we'll see uh, threading in Java, right? This is Java has that support for multi-threading, right? Java is one of the most mature and flexible threading models. So we have the Java.lang thread. The later, okay, so let's see. Uh, okay, this has a native OS level thread, so it is 1:1 modeling, right? Okay, and we need to understand. So basically, what is going? So this is we are going to have parallelism being now. Which thread is going to work? We that is the job of the scheduler, right? But here we can achieve 100% parallel. That is something. But then again, since it's 1:1, then should be a limit to how many threads you can do, right? So Java is most mature. So Java is, as we saw, Java inherently has that support, right? So multi-threading is inherently present in Java. So you have multi-threading inherently in Java. So this is inherently in Java. So this is a good thing, right? Now the thread to user to kernel modeling is 1:1. That means there is a limit on the number of threads you can create in Java. But then your true parallelism is what we achieve. So we have true parallelism is what we have here. Let's see, 1:1 model. Uh, so 1:1 model is yeah, so we have yeah, there is a limit, right? So I don't know how many we can create, but there is a limit to which you can create. Now there are two. Okay, we haven't talked about thread pool here, so but then yeah, that's okay. So right now we are only we are with. So there are two ways of creating threads. We'll see which to use one. Now ways to create thread. So we are now working with user level threads, right? The user level threads. Okay. So the way to create a user level thread in Java is first method is you can do it using thread class. Now it's, the second is implementing the Runnable interface. You implement the Runnable. The third way is basically when we are going to talk about using lambda expressions, right? So you can create a thread using lambda as well. So basically uh, using lambda. Now, so when we do using thread, so when we do using a thread class, we cannot extend this to other classes. Can't extend to other class. Can't extend to another class. Now this supports extension. So we can say and third, this is basically like a concise or a short way of creating a thread. Short and sweet. Okay. Mm, okay, that's all for introduction to threads. We'll see what is thread pool and then we'll see what is cooperative thread pooling with respect to shift GCD and we'll try to understand that little bit in detail, because that is the crux, right? Um, and we'll see the issues with threads, like what is going to happen, why threading or reactive, why threading and threading versus event loop to achieve the same thing. Okay, yeah, so that's all for this lecture. I hope you guys liked it. Please like and subscribe, and I'll see you in the next one. Till that time, take care. Bye bye.